This story is not about ready-made answers, but about the very structure of the knowledge we call the word cosmos. About how understanding of the universe takes shape when it is impossible to run an experiment and nothing can be repeated. About the fragile intersection of observations, models, and calculations that holds up everything we say about the world. This is a story not about what we know for certain, but about how we ever learn to tell knowledge apart from guesswork. At stake is the very form of our picture of reality, where the boundary lies between what has been measured and what has only been assumed. What it means to know when we speak of an object whose light travels for billions of years to reach us. What counts as reliable if 95% of what the universe is made of cannot be seen, caught, or touched? We will travel from the nearest star clusters to the very edges of the observable region. Look inside the interiors of stars where the atoms of our bones are born, and reach the places where the familiar laws of physics stop working in their usual form. Along the way, we will meet things described with high precision: the motion of planets, the evolution of stars, the formation of galaxies. And we will meet things whose nature remains open to this day: dark matter, the accelerated expansion of space, the earliest epochs. This journey will not end in any final answer, but within it, the outline will emerge of what science calls acknowledged uncertainty. And what would you do in the place of someone who looks up at the night sky and wants to understand how far one may trust knowledge? Which matters more, a stable description of what has already been measured, or honest silence where the data is not yet enough? This is not a story about sensations. It is a story about the quiet architecture of our knowledge of the universe. Listen, we are used to thinking that science is a set of finished answers. But knowledge of the cosmos is built differently. It is a living system of questions that never closes. Our picture of the universe did not take shape from a single discovery and did not arrive finished. It accumulated step by step through observations, calculations, miscalculations, and gradual refinements. Scientific knowledge of the cosmos differs fundamentally from mythological and philosophical constructions in that it rests on measurements, reproducible methods, and testable models. At the same time, it is never final. Every statement holds only as long as observational data agree with the calculations and no more accurate explanation has appeared. Modern understanding of the cosmos takes shape at the intersection of several fields of knowledge. Astronomy is concerned with the observation of celestial bodies and phenomena. Astrophysics studies the physical processes taking place in stars, galaxies, and the interstellar medium. Cosmology considers the universe as a whole, its origin, development, and large-scale structure. Each of these disciplines has its own instruments, but the boundaries between them are not rigid. They interact with and complement one another. Observation of the cosmos has long since moved beyond visible light. Modern telescopes work in the radio range, in the infrared, ultraviolet, X-ray, and gamma regions of the spectrum. This opens access to objects and phenomena that the human eye cannot distinguish. Cold gas clouds are found through their radio emission. The scorching regions near black holes reveal themselves in the X-ray range. Collisions of high-energy particles are recorded through gamma radiation. Each such window adds a fragment to the overall picture, but none of them alone completes it. Theoretical models play an important role in the study of the cosmos. They are built on the basis of known physical laws and allow one to predict the behavior of systems that cannot be studied directly. The evolution of a star, for example, is calculated using nuclear physics, thermodynamics, and the theory of gravity, and the results are then compared with observations of real stars at different stages of their lives. Agreement does not mean final truth, but disagreement always points to a need to revise the model. A distinctive feature of cosmic research is that direct experiment here is almost impossible. In a laboratory, conditions can be changed and an experiment repeated as many times as needed. In the cosmos, an observer deals with what exists on its own, beyond the reach of intervention. That is why many conclusions rest on statistics and on comparing a large number of objects. The properties of distant galaxies are studied through their radiation, which has traveled billions of light years. And such radiation carries information about the composition, motion, and age of the source, but requires careful interpretation. The scientific language strives for precision, yet behind that precision lies a sober awareness of uncertainty. In cosmology, it is customary to phrase statements in probabilistic terms. The mass of a galaxy, the age of a star, or the distance to an object is expressed not as a single number, but as a range of values, one that reflects the limitations of measuring instruments and the assumptions built into the model. The farther the object and the more complex the process, the wider that region of uncertainty. The same observation often allows several explanations. In such cases, science does not pick the most spectacular version, but weighs all options against the rest of the known data. An explanation that requires the introduction of new entities or the violation of already tested laws without dire necessity is treated with caution, but is not automatically discarded. The history of science has shown more than once that ideas long considered marginal ended up being confirmed. The universe is treated as a system governed by unified physical laws. It is assumed that processes taking place in distant galaxies are ruled by the same principles as phenomena near the Earth. This assumption is supported by observations, but it remains precisely an assumption, requiring constant testing. The structure of the solar system, the mechanism of thermonuclear reactions in stars, the role of gravity in the formation of galaxies, all of this is described in considerable detail. Whereas the nature of dark matter, the causes of the accelerated expansion of space, and the details of the early evolution of the universe still remain matters of debate. Knowledge of the cosmos is not a set of final answers, but a stable system of questions, models, and observations. It moves forward slowly, at times imperceptibly, through refinement of details and revision of assumptions. It is precisely this approach that allows a gradual approach to a more accurate understanding of the world's structure. And the first question that arises before us is this: how vast is the space that we are able to see at all? For long centuries, people looked at faint, hazy patches in the sky and did not suspect that each of them was an entire universe with hundreds of billions of its own suns. For a long time, the observable region of the sky was perceived as the entire existing universe. It was only at the beginning of the last century that it became clear that many hazy objects are not part of our galaxy, but separate stellar systems removed by colossal distances. From that moment, the picture of the scale of the world changed irreversibly. Instead of a limited set of stars, a space filled with billions of galaxies opened before us. The universe is described as a unified spacetime within which matter and energy are distributed. On the largest scales, it looks homogeneous and isotropic. When averaged over sufficiently large regions, the density of matter and the properties of space turn out to be approximately the same in all directions. This statement does not extend to individual galaxies or clusters. It holds only on scales exceeding the size of the largest structures. On smaller scales, galaxies are distributed anything but evenly. They form filaments, flat sheets, and dense clusters, between which stretch vast voids with sharply reduced density of matter. This complex network has come to be called the cosmic web. Its existence is confirmed both by direct observations and by computer models that account for the action of gravity over billions of years. The calculations show that even tiny initial inhomogeneities grow over time under the influence of gravity and give rise to large structures. The size of the observable universe is set not by its actual boundaries, but by the horizon, the limit up to which light has managed to reach the observer during the time that has passed since the beginning of cosmic expansion. Everything that lies beyond this horizon is inaccessible to direct study, since radiation from there has not yet reached the Earth. This does not mean that space ends beyond the observable region. Measuring distances in the cosmos is a separate and difficult task. For the nearest stars, the geometric method of parallax is used. For more distant objects, indirect approaches are applied, based on comparing brightness, spectral characteristics, and statistical regularities. Together, these methods form a ladder of distances, where each rung rests on the previous one. Errors on the lower rungs can propagate upward, which is why the methods are constantly refined and rechecked. One of the key discoveries was the finding that galaxies, on average, are moving away from one another. This should not be understood as motion of galaxies through motionless space in the ordinary sense. It is the expansion of spacetime itself, in which the distances between distant objects increase. The rate of this recession is proportional to the distance, a fact confirmed by spectral measurements of the radiation of galaxies. The structure of the universe is studied not only through the distribution of galaxies, but also through the background radiation that permeates all of space. This relic radiation, a remnant of an early epoch of the cosmos, carries information about the state of matter and the geometry of space at that time. Small inhomogeneities in its distribution correspond to those very initial disturbances from which galaxies and clusters later grew. Analysis of these data allows theoretical models to be tested with high precision. A description of the structure of the universe is always tied to a chosen model. The most widespread one assumes the existence of ordinary matter, dark matter, and a component responsible for the accelerated expansion. This scheme agrees well with most observations, but does not reveal the physical nature of the dark components. Despite significant progress, the structure of the universe remains a subject of active study. Parameters are being refined, alternative models are tested, deviations from expected behavior are tracked. Knowledge of the world's structure is a consistent yet unfinished picture. It leaves room for new data and new revisions. But what fills these galaxies? What are they made of? And how is a star born in the first place? Every atom of iron in our blood was once forged inside a dead star. Stars die so that new worlds can arise from their ashes. Knowledge of stars occupies a central place in the understanding of the cosmos, since it is precisely stars that are the main sources of radiation and energy in galaxies. Science treats a star not as a frozen dot in the sky, but as a physical system with its own life cycle. This cycle begins in the interstellar medium and lasts for billions of years, passing through stages that can be described on the basis of known physical laws. Interstellar space is not empty. It is filled with rarefied gas and dust that gather into clouds of varying density and temperature. In some regions, these clouds become dense enough for gravity to begin dominating over other forces, and then matter slowly contracts under its own weight. This process can drag on for a very long time and does not always end in the formation of a star. External influences, shock waves from the death of massive stars or collisions between clouds, can hasten the contraction and set it in motion. As contraction proceeds, the temperature in the central part of the future star gradually rises. In the early stages, the object does not yet sustain thermonuclear reactions. It exists as a protostar, surrounded by the remains of a gas and dust disk. During this period, the main share of the released energy comes from gravitational contraction. Such objects can be observed in the infrared range. It allows one to look through the dense dust clouds that hide the early stages of stellar birth from optical telescopes. The onset of thermonuclear reactions occurs at the moment when temperature and pressure in the core reach the required values. After that, the star enters a state of stable equilibrium. Gravitational contraction is balanced by the pressure that arises from the release of energy in nuclear fusion. This equilibrium can be maintained through most of the star's life, and its duration is determined by the mass of the object. More massive stars burn through their fuel reserves incomparably faster than their less massive counterparts. Stars rarely are born alone. More often they appear in groups, forming clusters. In such a cluster, all the objects are roughly the same age, but can differ greatly in mass and luminosity. This makes stellar clusters valuable laboratories for testing theoretical models of evolution. Within them, one can observe different stages of development under identical initial conditions of the environment. The gas and dust disk surrounding a young star gradually becomes a place where solid particles begin to stick together. They collide, combine, and gradually form ever larger bodies. This is how the foundations of planetary systems are laid. This process depends on many factors: the mass of the star, the composition of the disk, and the dynamics of matter. Modern observations convincingly show that planetary systems are the rule, not a rare exception. Studies of exoplanets have radically changed the view of what configurations of stellar systems are possible. Systems have been found that differ strikingly from the solar one. Some planets orbit very close to their star, others have elongated orbits, or unusual combinations of masses and distances. All of this indicates that the processes of formation and subsequent evolution of planets can lead to a wide diversity of final architectures. A star's life is not eternal. As nuclear fuel is exhausted, the internal equilibrium is disrupted. The star's further fate is determined by its mass. Less massive objects gradually shed their outer shells, leaving a compact core behind, whereas more massive ones pass through sharp changes in structure and energy balance. In both cases, the star returns matter to the interstellar medium, enriching it with heavy elements. In this way, a continuous cycle closes, linking the birth and death of stars with the evolution of galaxies as a whole. Stars do not exist in isolation. They gather into vast islands. What is a galaxy, and how does it live through time? Galaxies look static in photographs, but on the scale of cosmic time, they are living beings. They grow, swallow one another, and slowly fade. Galaxies are large, gravitationally bound systems that unite stars, gas, dust, and components whose nature is not fully established. Studying them made it possible to move from consideration of individual stars to a view of the cosmos as a hierarchical structure in which objects are combined into systems of increasing scale. Galaxies differ in shape, mass, composition, and history of development. This diversity is itself a subject of research. The most widespread classification of galaxies is based on their morphology. Disk systems with spiral structure, more compact elliptical forms, and systems with an irregular distribution of matter are distinguished. However, this classification is not rigid. The shape of a galaxy can change over time. Observation of distant objects shows that in the early epochs of the cosmos, galaxies often had distorted and unstable structure, evidence of active processes of interaction and formation. The origin of galaxies is tied to the evolution of density inhomogeneities in the early universe. Small variations in the density of matter were amplified over time under the action of gravity. In the denser regions, gas and dark matter began to collect, forming potential wells in which the first stars later arose. This process proceeded unevenly, depending on local conditions, which is what produced the diversity of galactic structures. Interactions and mergers play an important role in the evolution of galaxies. Galaxies often exist in groups and clusters, where gravitational interactions are unavoidable. The approach of two systems is able to deform their outlines, intensify the birth of new stars, and redistribute matter. In a number of cases, the interaction ends in a complete merger. A more massive system is formed with different characteristics. The evolution of a galaxy is closely connected with the rates of star formation. In their young epochs, many galaxies possessed large reserves of cold gas that fueled active star birth. Over time, the gas is spent or heated, the rate of star formation falls, and the galaxy gradually changes its appearance, color, spectrum of radiation, internal dynamics. At the centers of many galaxies sit compact objects of enormous mass. Their presence is revealed through the character of the motion of stars and gas in the inner regions. Active phases of such objects, accompanied by powerful radiation, are able to change the state of the interstellar gas and regulate the rates of star formation throughout the galaxy. Environment, too, influences the evolution of a galaxy. In dense clusters, galaxies more often lose gas, experience frequent interactions, and pass more quickly into a state of low activity. In isolated regions of the cosmos, evolution proceeds more slowly and more evenly. Observation of distant galaxies is a literal look into the past of the universe. Light from them carries information about earlier states, allowing the history of their development to be traced over billions of years. Galaxies appear as dynamical systems whose fate is determined by a combination of internal processes and external influences. And understanding of this evolution continues to be refined as new data accumulate. What kind of object hides at the center of a galaxy? And why can not even light escape from its pull? In space, there is a boundary beyond which not even light comes back. What happens behind it, we do not know, and perhaps we never will. For a long time, black holes existed only as a mathematical consequence of the equations of gravity, before they became an object of observational astrophysics, and their modern understanding took shape at the intersection of the general theory of relativity, astrophysics, and observational data. These objects are treated not as exotic exceptions, but as a regular outcome of the evolution of massive stars and the dynamics of dense regions of galaxies. A black hole is defined not by a material surface, but by a region of spacetime out of which nothing is able to cross a certain boundary. This boundary is called the event horizon. It is not a solid shell, it is a geometric property of spacetime. To an outside observer, processes near the horizon look strongly distorted because of gravitational effects and time dilation. The formation of black holes is tied to the collapse of massive stars. After nuclear reactions in the core cease, internal pressure ceases to withstand gravitational contraction. If the mass of the remaining matter exceeds a certain limit, contraction continues to a state in which an event horizon appears. The further fate of the matter is described no longer in the categories of ordinary physics of matter, but in terms of the geometry of spacetime. Observation of black holes is carried out by indirect methods. They do not shine, but their presence shows up through their effect on the surrounding matter. Gas falling into the gravitational trap heats up to colossal temperatures and begins to radiate in high-energy ranges. The motion of stars near the center of a galaxy allows the mass of the compact object hidden in its nucleus to be estimated. Such observations show that at the centers of many galaxies sit supermassive black holes whose mass exceeds that of the Sun many times over. Of particular interest are the extreme conditions that arise near the event horizon. Their density, temperature, and curvature of space reach values at which the usual notions about the behavior of matter cease to work. Theoretical models describe the inner region of a black hole as a zone where the classical laws of physics are inapplicable in their usual form. However, no direct observations of these regions exist. Any statements about them remain conclusions based on the extrapolation of known theories. Black holes differ in mass and origin. Besides stellar and supermassive objects, the possibility of the existence of intermediate mass black holes is discussed. Their presence is confirmed less confidently and remains a subject of research. Hypotheses about primordial black holes, presumably arising in the earliest stages of the universe's evolution, are also considered. These ideas have not yet received unambiguous confirmation, but they continue to be discussed in the scientific community. Gravitational waves have opened a fundamentally new channel for the study of black holes. Oscillations of spacetime that arise in the merger of compact objects make it possible to obtain information about their masses and properties. These data supplement the picture compiled from electromagnetic observations and allow theoretical predictions to be tested in regimes previously inaccessible to research. Thus, black holes become natural laboratories for the study of gravity and matter in conditions of extreme extremity. While a significant part of what is known about them still rests on indirect data and theoretical models, leaving room for uncertainty and further development of understanding. But black holes are not the only invisible thing that shapes the form of the universe. There is something even more mysterious. About 95% of what the universe is made of cannot be seen, caught, or studied directly. We know it exists only because it warps space around itself. Observable matter makes up only a small fraction of what takes part in shaping the gravitational structure of the universe. This became clear when measurements of the motion of stars and galaxies ceased to agree with what could be expected from the distribution of visible matter. It became necessary to assume the existence of a component that emits no light, practically does not interact with electromagnetic radiation, but exerts a gravitational effect. The first indications of the presence of dark matter appeared in the study of the motion of stars in galaxies. The rotation speeds of stellar disks turned out to be higher than followed from the mass of the observable matter. Similar discrepancies were also found in the analysis of the motion of galaxies within clusters. All of this pointed to the presence of additional mass, distributed over a more extended region than the visible structures. Dark matter does not yield to direct detection. It emits and absorbs no light in any known range. Everything that is known about it is inferred from gravitational effects. In particular, the bending of the paths of light from distant objects as it passes near massive structures makes it possible to map the distribution of mass independently of its visibility. Such observations invariably show that the mass in galaxies and clusters significantly exceeds the total mass of stars and gas. According to modern cosmological models, dark matter played a key role in the formation of the structure of the universe. It was precisely this component that created the gravitational scaffolds in which ordinary matter later accumulated. Computer calculations show that without this component, the observed distribution of galaxies cannot be reproduced. At the same time, the properties of dark matter in the models are set so as to agree with the available data. However, its physical nature remains unknown. There are several hypotheses about what it may consist of. One group of ideas assumes the existence of new elementary particles that interact weakly with ordinary matter. They are actively being sought in laboratory experiments and astrophysical observations. Another group considers the possibility that the observed effects are explained by a change in the laws of gravity on large scales, without the introduction of an additional invisible substance. Neither of these hypotheses has yet received a final confirmation. Direct experiments to detect particles of dark matter have not produced unambiguous results, while alternative theories of gravity successfully describe part of the observations, but run into difficulties in trying to cover the whole of them. Besides dark matter, other invisible constituents of the cosmos are also discussed. To explain the accelerated expansion of space, an additional component is introduced, tied to the dynamics of spacetime itself. Its influence appears only on the largest scales and practically does not affect local processes. The nature of this component also remains a matter of debate. The study of the invisible constituents of the cosmos requires a combination of different approaches: observations of galaxies and clusters, analysis of relic radiation, particle experiments, and the development of theoretical models. Each of them has its limitations, but together they gradually narrow the range of possible explanations. But what is this space itself? And what is time in which the entire history of the universe unfolds? Time does not flow the same for everyone. Near a very massive object, 1 hour can correspond to millennia outside. This is not fantasy, it is a confirmed fact. The understanding of space and time in a cosmic context differs strikingly from everyday intuitions. Modern physics regards them not as independent and unchanging entities, but as an interconnected structure whose properties are determined by the distribution of matter and energy. This view became the basis for explaining a multitude of observed phenomena in astronomy and cosmology. Space and time are united into a single structure, spacetime. In this system, the motion of bodies and the propagation of radiation are determined by its geometry, which can change under the action of masses and flows of energy. Gravity in this understanding is not a force in the usual sense, but a consequence of the curvature of spacetime. It is precisely this that explains the orbits of planets, the deflection of light near massive objects, and the difference in the passage of clocks in different gravitational conditions. Observations confirm that the passage of time is not the same everywhere. Near heavy objects and at high speeds, time runs differently than in quiet regions of space. These effects have been tested experimentally many times and are taken into account in precise measurements. In the cosmos, they show up especially markedly. Their masses and speeds can exceed terrestrial values by orders of magnitude. The expansion of the cosmos is a change in the very geometry of spacetime. It does not reduce to the motion of galaxies through motionless emptiness, but means that the distances between distant regions increase. This expansion affects the propagation of light, stretching its wavelength. Observation of such stretching makes it possible to study the history of cosmic expansion and to reconstruct the properties of spacetime in different epochs. The question of the beginning of time remains complex and manifold. Within the framework of standard cosmological models, time is regarded as a quantity that has a certain initial moment associated with a very dense and hot state of the early universe. However, physical laws near this state are described incompletely, and therefore any statements about the nature of time at the earliest stages are formulated with great caution. Various approaches are considered in which the very concept of time may have a more complex structure. On ultra-small scales, space-time may behave differently than classical theory predicts. A number of theoretical models assume that at extremely small distances, space-time reveals quantum properties. These ideas do not yet have direct experimental confirmation, but they are being actively investigated. They may become a key to unifying gravity with other fundamental interactions. The cosmos provides a unique opportunity to test ideas about space and time. Observation of compact, massive systems and other extreme objects makes it possible to study effects that cannot be reproduced in a laboratory. The distortion of time in gravitational fields and the dependence of the passage of clocks on speed have been confirmed many times. Questions about the quantum structure of spacetime, the nature of singularities, and possible additional dimensions remain open and are discussed within the framework of various theoretical approaches. If spacetime is the fabric of the cosmos itself, then what is matter made of? Where did all the atoms that make up our own bodies come from? We are stardust in the literal sense. The calcium atoms in our bones and the oxygen in our breath were synthesized in dead stars billions of years ago. The chemical composition of the universe is neither random nor unchanging. It took shape gradually through processes that span the whole history of the cosmos. Modern understanding of the origin of chemical elements rests on a combination of observations, nuclear physics, and models of stellar evolution. These data make it possible to trace how, from the simplest forms of matter, the diversity of elements we observe today arose. At the earliest stages of the universe's existence, matter was in a state of extreme density and temperature. Under such conditions, only the simplest nuclei could exist. As space expanded and cooled, nuclear reactions became possible, in the course of which light elements were formed. The main part of matter consisted of nuclei of hydrogen and helium, along with small admixtures of heavier nuclei. This ratio is confirmed by both theoretical calculations and observations of the chemical composition of the oldest stars and of the intergalactic gas. Heavier elements could not arise in significant quantities at this early stage. Their formation is linked to processes that unfold in the depths of stars. In stellar cores, at sufficiently high temperatures and pressures, successive nuclear transformations unfold, in which light elements are gradually converted into heavier ones. The set of elements synthesized by a star is determined by its mass and stage of evolution. As the star ages and the conditions in its depths change, new chains of reactions are set in motion. In massive stars, elements up to iron are formed in this way. The formation of nuclei heavier than iron requires special conditions, the rapid capture of particles at large flows of energy. Such conditions are realized in the rare and short-lived events that accompany the final stages of the life of some stars. The synthesized elements are dispersed in interstellar space through the ejection of matter. Stars in the late stages of life gradually shed their outer shells, enriching the surrounding environment with new elements. In more extreme cases, this happens in the course of powerful, explosive processes. They not only redistribute the elements, but also create, in the interstellar medium, the conditions for the birth of new generations of stars. The chemical evolution of galaxies reflects the accumulation of these processes over billions of years. Old stars, formed at the early stages, contain few heavy elements. Young ones are born from matter already enriched by previous generations. Therefore, the chemical composition of a star serves as an indicator of its age and of the history of the system in which it arose. The interstellar medium, too, actively participates in chemical evolution. In cold clouds of gas and dust, reactions take place that lead to the formation of molecules, including fairly complex compounds. Their presence is recorded by means of radio observations in spectroscopy. This shows that chemical complexity is able to arise in conditions far removed from stellar interiors. The details of the formation of the heaviest elements are not fully clarified. Various scenarios are discussed in which different types of astrophysical events may play a key role, and observational data are gradually refining these models, though a unified description is only just taking shape. The origin of the elements in the cosmos is a long, many-step process linking the physics of the microworld with the large-scale evolution of the universe, and showing how chemical diversity grows out of a limited set of initial conditions. If the building blocks of life are scattered across the whole universe, could life have arisen somewhere else? Right now, possibly, beneath the icy crust of one of Jupiter's moons, an ocean sloshes, and no one knows whether it is empty. The question of life beyond the Earth occupies a special place in scientific studies of the cosmos. It lies at the intersection of astronomy, biology, chemistry, and physics. Modern science approaches it not through the search for direct proof of the existence of life, but through the study of the conditions in which it may originate and persist. Such an approach allows one to gradually narrow the region of uncertainty without stepping outside the bounds of testable data. One of the key conditions for life in the customary earthly sense is considered to be the presence of liquid water, because of its role as a universal solvent and as a medium for complex chemical reactions. Observations show that water in various forms is widespread in the cosmos. It is found in interstellar clouds, in the neighborhoods of young stars, on the moons of planets, and in the composition of comets. This testifies to the fact that the basic chemical component necessary for known forms of life is not at all a rarity. Studies of planetary systems beyond the solar one show that planets are found around stars of the most varied types. Many of them are comparable in size to the Earth and are located at distances at which the surface temperature can allow water to exist in a liquid state. Such regions are usually called zones of moderate temperature. However, their very presence does not yet mean that suitable conditions for life have actually taken shape on a planet. The composition of the atmosphere, internal sources of energy, and the stability of climate also play an important role. Within the solar system, too, a number of objects are considered that hold interest from a biological point of view. Some moons of the giant planets show signs of the presence of subsurface layers of liquid. These environments are isolated from the surface, but they can receive energy through internal processes. Such conditions differ from earthly ones, but they show that possible niches for life are not limited to the surfaces of planets. The chemical prerequisites of life are investigated through the analysis of organic molecules in the cosmos. In the interstellar medium, compounds are found that contain carbon, hydrogen, oxygen, and nitrogen. These molecules are able to form in cold clouds and to persist over long periods of time. Their presence indicates that the basic building blocks of complex chemistry arise naturally, without the participation of biological processes. At the same time, it is important to distinguish between the possibility of the origin of life and its further development. Even in the presence of suitable conditions, it remains unclear how likely the transition from complex chemistry to self-replicating systems is. This stage remains one of the least understood. There exist various models describing possible paths of such a transition, but none of them can be tested directly on a cosmic scale. The search for signs of life beyond the Earth is conducted by indirect methods. Analysis of the atmospheres of exoplanets makes it possible to detect chemical compounds that in certain combinations may point to active processes. However, such signs can also have non-biological explanations, and therefore any such observations require careful interpretation and comparison with physical and chemical models. A separate direction of research is tied to the search for technological activity. It assumes the possibility of detecting artificial signals or structures, rests on strict criteria of data analysis, and does not proceed from any a priori conclusions. The absence of detections is not yet regarded as proof of the absence of life. It only reflects the limitations of the applied methods and of the coverage of observations. So what, in the end, do we know about the cosmos? And where does knowledge end and honest, acknowledged uncertainty begin? Modern knowledge of the cosmos is built on a foundation of extensive observations, theoretical models, and tested physical laws. At the same time, science clearly distinguishes between the areas in which understanding is sufficiently stable and those stretches in which uncertainty remains high. This distinction is not a sign of weakness of the scientific approach, but its integral component, one that makes it possible to separate well-founded conclusions from assumptions. The general regularities of the motion of celestial bodies, the evolution of stars, the formation of galactic structures, and the chemical development of matter are well described. The models describing these processes successfully agree with observations across a wide range of conditions. Their parameters are being refined, but the principles themselves remain stable. They form a reliable framework on which everything else rests. One of the key zones of uncertainty remains the nature of the components that are not observed directly. Dark matter is introduced to explain a consistent set of data, but its physical essence has not yet been established. Existing models effectively describe the observed structure of the universe while allowing different interpretations. At the present stage, it is impossible to state unequivocally whether the accepted description is final or only an approximation to the truth. Substantial limitations are tied to the very possibilities of observation. The cosmos is accessible to study only through radiation and rare indirect signals, relic radiation, the light of distant galaxies, signals from the interstellar medium. Many processes unfold on scales of time and energy that are unreachable for direct experiment. This forces the extrapolation of known laws into regions where their applicability may be limited. Such extrapolations are necessary, but they are always accompanied by reservations. A separate layer of uncertainty is tied to the very earliest epochs of the cosmos's existence. The description of these states rests on theories that work successfully in other conditions, but have not been tested in such extreme regimes. Therefore, the models of the initial stages of the universe's evolution are regarded as working hypotheses rather than as finished descriptions. Different approaches at times lead to similar, observable consequences, which makes their distinction difficult. The boundaries of knowledge show up also in questions tied to the unification of physical theories. Modern physics has at its disposal several fundamental descriptions, each of which works successfully on its own level, from quantum scales to the cosmic web and the black holes that warp spacetime. However, their unification into a single system remains an unsolved task. The cosmos provides an environment where effects of different scales intersect, but access to such regimes is still limited. Uncertainty in the scientific sense is not equivalent to arbitrariness. It has clear limits, set by the data and by the logic of the theory. Science distinguishes between what is completely unknown and what is known in part. In the first case, questions are formulated and directions of search are marked out. In the second case, parameters and the boundaries of applicability of existing models are refined. The development of cosmic research steadily pushes back the limits of knowledge. New instruments give more accurate data, expand the range of observations, and make it possible to test assumptions previously unreachable for experiment. At the same time, every new level of detail often lays bare questions that were not obvious before. This makes the process of learning continuous and fundamentally open. Science describes many sides of the universe's structure with confidence, while acknowledging the areas in which answers have not yet taken shape. Such a state is not a temporary failure, but a reflection of the very nature of the scientific approach, in which understanding expands gradually, without final points in closed topics. Science leaves questions about dark matter in the early universe open. Do you consider this the right path?